Every year, more than 15 billion trees are cut down across the planet, completely disrupting forests and natural ecosystems. Yet this process unfolds almost in silence because it fuels a trillion-dollar global timber industry, supplying materials for housing, furniture, infrastructure, and nearly every corner of modern life. Behind every smooth wooden board lies a massive industrial chain, from harvesting machines weighing tens of tons, working deep inside forests, to automated cutting, hauling, and debarking systems, and finally sawmills operating day and night with precision down to the millimeter. So how does the modern timber industry really work? And how do humans extract forests on such an enormous scale? Let's find out with Mandarin Tech. In the United States, harvesting forests made up of tree species such as pine, oak, and birch not only provides an abundant supply of raw materials, but also ensures the high quality required for paper production. At the heart of the wood harvesting process is the harvester, a highly versatile machine engineered with specialized features. It is capable of processing up to 200 metric tons of wood per hour, a record-breaking speed within the industry. These machines can handle trees with a maximum diameter of 80 centimeters, although in practice they most commonly process trees ranging from 10 to 30 centimeters in diameter, which are ideal for paper manufacturing. Unlike the massive feller buncher, which focuses solely on cutting and grouping trees, the harvester excels at multitasking. It seamlessly integrates multiple operations, including cutting, gripping, trimming branches, removing foliage, and segmenting trunks into standardized log lengths, consolidating what was once a multi-step process into a single, streamlined operation. The harvester's advanced hydraulic system enables rapid and precise movements, while its automated sensor technology accurately identifies each tree and adjusts operations based on its dimensions. Its cutting head, equipped with high-efficiency blades, swiftly removes branches and foliage, minimizing waste and dramatically increasing processing speed. After the harvester finishes its work, the forwarder takes over the entire task of collecting and transporting processed logs out of the forest. Designed to operate efficiently in rough and complex terrain, the forwarder can move through mud, steep slopes, and unstable ground without damaging the forest floor or the surrounding vegetation. Thanks to its tracked or low-pressure tire system combined with a balanced chassis, the forwarder is able to carry large volumes of timber in each trip with stability and safety. This capability not only helps preserve the forest's ecological structure, but also ensures a continuous and reliable flow of raw material to paper mills and other wood processing industries. By serving this critical intermediary role, the forwarder keeps the entire logging operation running smoothly. As a result, the industry can reach massive production levels, up to 15 million tons of timber, while still minimizing negative impacts on forest ecosystems. In areas with steep or uneven terrain, skidders become the primary workhorses. Like the senior members of a logging crew, skidders step in to replace forwarders, ensuring that timber transport remains continuous and efficient. Equipped with powerful engines producing up to 700 horsepower, along with specialized tracked or articulated wheel systems and advanced hydraulics, skidders are built to handle the harshest forest environments. This robust design allows them to operate reliably in muddy conditions, on steep slopes, and across rugged terrain, places where conventional vehicles simply cannot reach. As a result, even the most remote and challenging logging sites can be accessed and harvested safely and effectively. And now, let's immerse ourselves in the raw, authentic sounds of logging operations. Deep within the vast forests of the United States. Harvesters, forwarders, and even skidders. These modern machines have entered the forestry industry and triggered a complete revolution. By replacing hand axes with mechanical power and advanced technology, They have transformed logging from dangerous, labor-intensive work into a precise and highly efficient operational system. As a result, productivity has reached unprecedented levels, costs have been optimized, and the entire timber supply chain has accelerated. After leaving the forest, the massive logs are gathered at the sawmill's log yard. This is an immense open space where hundreds of trunks are stacked in long rows, like giant stockpiles waiting to begin their transformation. To preserve quality, many mills spray water continuously over the logs or submerge them in holding ponds, preventing cracks and protecting them from mold before processing. From the yard, the logs move on to sorting. Workers and laser scanners work together to assess each trunk, identifying the species of wood, measuring its diameter, and checking for defects or warping. Logs with the best characteristics are reserved for top-grade lumber, while those with more knots, greater curvature, or visible cracks are directed to other uses where such imperfections matter less. This entire process not only maximizes economic efficiency, but also demonstrates the precision of extracting value from every log, ensuring that no part goes to waste. Before the logs meet the saw blades, many of them pass through a debarking machine. The rough outer layer, often filled with soil and insects, not only wears down the steel, but also affects the finish of the lumber. Debarking is most commonly applied to softwoods such as pine, fir, or spruce, the dominant species in construction, where consistency and stability are essential. In smaller workshops or for handcrafted products, logs are sometimes sawn directly and surface-treated later, and in some cases, the bark is even left on to preserve a rustic, natural look. This process produces countless tiny wood chips, and not a single piece is wasted. Every fragment is collected and sent into the next stage of production, embodying the principle of making full use of resources and moving towards sustainability. How these fragments are ultimately repurposed is something you'll see more clearly at the very end of this journey. Once a log is secured on the conveyor, a laser scanner sweeps across its entire length. Red beams record every detail: diameter, curvature, off-center alignment, even the large knots that could affect the cut. From this data, specialized software creates a three-dimensional model and runs multiple cutting scenarios. Within seconds, the computer selects the optimal pattern, maximizing usable volume while preserving quality. With the cutting map ready, the log moves into a high-powered bandsaw. Depending on the requirements, the mill may choose plain sawn cuts, slicing parallel along the log's length to produce high volume with sweeping grain patterns, though more prone to warping over time. Or quarter sawn cuts, splitting the log into 4 sections before sawing each, yielding straight, even grain with greater stability and higher value, though at the cost of lower yield and more labor. These two methods embody the constant balance between economic efficiency and long-term quality. Immediately after the method is chosen, the breakdown sawing begins. Steel blades, sometimes more than 10 feet long, roar to life, slicing massive logs into larger slabs, often wide planks or semi-finished blocks. This is the stage where the log is opened, separating its core from its outer sections and preparing it for edging and precise trimming. The slabs are neatly stacked on the conveyor, ready for the next stage. Throughout the process, an automated system monitors every detail. Blade speed, vibration, and the thickness of each cut are continuously measured and adjusted by sensors. Amid the thunderous sound of steel biting into wood, the first rough planks emerge from a once whole log, the earliest form of lumber, marking the true beginning of its transformation. From the breakdown stage, the large slabs continue down the conveyor to the precision saw line. Here, narrower and sharper blades are used to resaw the slabs into boards with exact thickness. This process, known as resawing, transforms rough blocks into commercial-grade lumber, with thickness ranging anywhere from just over an inch to more than 4 inches, depending on the intended use. Every cut is tracked by sensors, keeping the margin of error close to zero. Once the rough boards are produced, the next step is edging. The uneven, irregular sides near the bark are trimmed away by auxiliary saws, to create clean, square edges. After edging, each board can be stacked, transported, and processed with ease. Even the discarded strips are not wasted. They are collected and repurposed into particle board, plywood, or biomass fuel. At this stage, the slabs have become flat, straight-edged boards, lumber stacked in seemingly endless rows. Throughout the process, technicians monitor operations on site, performing random inspections on each batch to ensure that every board meets exact specifications before moving on to the following stages. After sawing and edging, lumber still retains a high level of natural moisture, sometimes nearly half its weight. If left untreated, the wood would easily warp, crack, or deform during use. To stabilize its structure, the boards are neatly stacked before being placed into the kiln. Thin wooden spacers are laid between each layer, creating gaps that allow heated air to circulate evenly, helping the entire batch dry consistently from the inside out. Inside the kiln, powerful fans push hot air through those gaps in constant circulation. Temperatures can range from 120 degrees Fahrenheit up to more than 210, depending on the species and the final purpose of the wood. At the same time, humidity inside the chamber is carefully regulated. At the beginning, moisture is drawn out quickly, while later the pace is slowed so that the core dries in harmony with the surface, preventing splits. The goal of drying is to bring the wood's moisture content to an ideal range, about 15 to 19% for construction lumber, and as low as 6 to 8% for high-grade furniture. This makes the lumber lighter to transport, more stable to build with, and more resistant to weather, while also reducing the damp conditions that allow mold or insects to thrive. It is the step that transforms green, fragile wood into a safe and durable material. After being dried and planed smooth, the finished lumber is sent to the packaging area. Here, automated conveyors stack the boards into neat bundles, ranging from a few dozen to several hundred pieces, aligned so that every edge matches perfectly. Hydraulic arms compress the stack, while steel bands or heavy-duty plastic straps are wrapped tightly around it, turning the bundle into a solid block that can weigh up to several tons. To protect the wood from moisture during storage and transport, the outer surfaces of each bundle are often wrapped in thick plastic sheeting or covered with waterproof tarps. Some mills go further, enclosing the stacks in wooden frames for extra safety, especially for long-distance export shipments. Each bundle is clearly labeled with details such as wood species, dimensions, production date, and destination, ensuring easy traceability and distribution. Finally, forklifts load the secured bundles onto trucks or into containers. The entire process is designed to prevent shifting, warping, or damage before the lumber reaches its final users. While finished lumber bundles leave the mill, the side streams, wood chips, offcuts, and sawdust are far from waste. Instead, they begin a parallel journey, transformed into a man-made material known as MDF, an engineered wood now found in buildings and furniture everywhere. The first step is collection and primary cleaning. Scraps from across the mill are gathered into holding yards, then passed through magnets and screens to remove nails, stones, or other contaminants. Only clean wood remains. Immediately after, the material is ground in high-speed disc refiners, breaking it down from chips into fine, uniform wood fibers. These fibers form the very foundation of MDF. Next, the fibers enter a mixing chamber where ultra-fine sprays coat each strand with urea formaldehyde or melamine urea formaldehyde resin. This gives every fiber a binding jacket, ready to lock together into a solid mass. Depending on the application, moisture-resistant or fire-retardant additives may be introduced at this stage. The fiber resin blend is then spread into a thick mat across a long conveyor. Rollers compress it lightly, creating a sheet many times thicker than the final product. In the hot press stage, the mat is subjected to pressures of several hundred tons and temperatures exceeding 400 degrees Fahrenheit. Within minutes, the resin liquefies, flows between the fibers, and then hardens again, fusing millions of strands into one unified board. This is the moment MDF is truly born. Once it leaves the press, the panel is cooled gradually to prevent warping, then trimmed to precise dimensions by edge-cutting saws. The final step is multi-stage sanding, which levels both surfaces to a near-perfect smoothness, ready for veneer, melamine, or paint finishes. From what once were mere leftovers of lumber production, a new material emerges, stable, versatile, and deeply embedded in modern life. MDF not only maximizes the value of every tree harvested, but also extends the story of wood far beyond the sawmill floor. And with that, we've reached the end of our journey through the modern logging industry, from deep within the forests to the construction sites where timber takes on new life. If you found this video helpful, don't forget to hit like to support Mandarin Tech. And if there's anything we may have missed, feel free to share your thoughts in the comments. Thank you for watching. Goodbye, and we'll see you in the next Mandarin Tech video.